Hello everyone, myself Dr. Sanjay Kumar Suman, Professor Department of ECE and Dean R&D, St. Martin's Engineering College, Sikandrabad, Telangana. I welcome you all to my series of video session that is a digital electronics I am taking. Today's topic is counter design. Today's topic will take counter design. Here we'll take basic and design part both. In basic part, this is my overview of today's lecture. We'll start with the definition of the counter, followed by the characteristic of the counter, and we take a ripple counter, one design part, then ripple down counter, then synchronous counter, followed by a small video session. So we'll start with the overview of counter. Counter is a electronic device which counts the pulses. Basically, it counts the pulses which is applied to the flip-flop or applied to the pulse input of the counter. And it has many applications. Even pulse also can be counted. If counter is embedded with the sensor, then heart pulse also can be counted. It is used for the digital clock. Can be used for the frequency division, analog to digital converter, and addressing the memory location. So there are many applications of the counter. So if we move to the characteristics of the counter, counter can be of 2-bit counter, 4-bit counter, 16-bit counter, and 2 to the power of n-bit counter. So all the counter, 2-bit counter means it requires 2 flip-flop, 4-bit counter means it requires 4 flip-flop, 8-bit counter means it requires 8 flip-flop. So as many bit counter you need, that many flip-flop it requires. And basically 2 types of flip-flop required to design the counter. D flip-flop also can be used, SR flip-flop also can be used, but JK flip-flop and T flip-flop is meant for designing the counter. So 2 flip-flops are used for designing the counter. Why it is used? I'll tell you that because of its toggle its toggle property. Then how many states one counter counts? 2-bit flip-flop will count 2 to the power of 2. That means 4 states. 4-bit counter will count 16 states. 5-bit counter will count 2 to the power of 5, 32 states. So 2 to the power, the number of n is given, that 2 to the power of n states it counts. There are 3 types of counter. One is a synchronous counter, one is a synchronous counter, one is a special type of counter which is ring counter and Johnson counter. Here we focus on the asynchronous counter now. Asynchronous counter, and we have a small difference between ripple counter and synchronous counter. Asynchronous counter is also called as a ripple counter. Ripple counter means here ripple counter. Suppose there are 4-bit counters. With 4-bit counter, first flip-flop will be given the clock pulse. Remaining flip-flop will not be given clock pulse directly. Second flip-flop clock pulse will be taken from the output of previous flip-flop. Similarly, third flip-flop clock pulse will be taken from the output of previous flip-flop. Therefore, only first flip-flop will be given the clock pulse. Remaining all other flip-flop, next to next flip-flop will be driven by the previous flip-flop. Therefore, it is not synchronized. It is a asynchronous counter. Whereas in synchronous counter, all the flip-flop will be given clock commonly. Single clock pulse can control all the flip-flop. This is the difference. Therefore, asynchronous counter is little bit slower than synchronous counter. Here I'll show you the one difference between these two. Here itself I can show that asynchronous counter, synchronous counter difference I'll show you. Here is one flip-flop, second flip-flop, third flip-flop. I take example of 3 flip-flop, 3-bit counter. Here I am giving the clock pulse Q, J, K, Q bar. From here we take the clock pulse here. Here we take the clock pulse to drive the second clock pulse. J2, K2, Q2, Q2 bar. Similarly, third clock pulse will get clock from the previous one. So this is the method of the asynchronous counter. Whereas in synchronous counter, all flip-flop will get the common clock pulse. This is the basic difference of the synchronous and asynchronous counter. This is the basic difference of synchronous and asynchronous counter. Here, this is the basic difference, synchronous and asynchronous counter. We'll move back to next. We have explained all the basic thing. Difference explained. Next we will see the ripple counter. Ripple counter also a synchronous counter. Here we will see the design. Here we have taken example of 4-bit asynchronous counter. In 4-bit asynchronous counter, 4 JK flip-flop we have taken. In this, all the 4 JK flip-flop will keep in toggle mode. Toggle mode means both J and K, when input of both J and K will be taken as a, when input of both J and K will be connected to the 1, then it is called the toggle mode. For example, here is J, here is K, Q, Q bar, both J, K will give 1, then output will keep toggling at each clock pulse. Here I am giving clock pulse CP1. If it was a 0, the 0 will become 1. When you give CP2, if it was 1, this will become 0. So this is called toggle mode of the JK flip-flop. It will always toggle when J and K will be connected to 1 and the clock pulse will be given. So in this clock pulse here, preset and clear we inactive now. It will be used for designing the modulus of the counter. Now you are seeing here all the J and K are in toggle mode. We have given pulse 1. When you have given pulse 1, this was 0 before, the 0 will become 1 now. All others are 0, 0, 0. When you give the pulse 2, while giving pulse 2, first flip-flop will always toggle. So it was a 0, became 1, again became 0. But before the transition of the next clock pulse, here it was 1, that 1 drives this clock pulse also in toggle mode. At the application of clock pulse, this also toggled. So this also became 1. Again in next pulse, pulse 3 when we are giving, pulse 3 after giving pulse 3, this will toggle every time. This will toggle every second time. So here it is 1, 1. See this relationship between pulse and output. When we are given third pulse, it is displaying here 3. When we are giving fourth pulse, it is displaying here 4 in binary. When you are giving fifth pulse, it is displaying 101. When you are giving sixth pulse, it is displaying 110. When you are displaying the seventh pulse, it is here it is 111. Up to this 1, 2, 3, all the 3 flip-flop has been toggled. Last one is not all toggled right now. Now in next clock pulse when you give, then all flip-flop will toggle at the 8th clock pulse. This will become 1, this will be 0, this will be 0, and this will be 0. So 8th clock pulse is very important here. At the 8th clock pulse, all the flip-flop will toggle. On the next clock pulse, all the flip-flop will toggle because every flip-flop will get high to low input. So we are giving the 8th clock pulse, this changes, this changes, this changes, and this also changes. So likewise, it will count up to 1 to 16 clock pulse. 4-bit flip-flop will count up to 16 clock pulse. Similarly, now we'll show some example we'll give for the modulus of counter. For modulus of counter, we'll take one small example. Same flip-flop, same up counter can be used as a modulus of counter. Like a 3-bit flip-flop, once again I am taking example. This is 3-bit flip-flop. 1 flip-flop, 2, then 3. 3 flip-flops are used to design a 3-bit counter. We'll use here clock pulse, negative edge clock pulse. We'll use clock pulse, Q2, Q2 bar, Q1, Q1 bar, J1, K1, J2, K2, J3, K3, Q3, Q3 bar. I've connected here. Output connected as a clock pulse to next. Both J and K made as a 1. Both J and K made as a 1. Both J and K made as a 1. And here clock pulse I am giving. So this 3-bit counter will count 0, 0, 0, 0, 0, 0 to 1, 1, 1. Total 8 state it will count. Now same counter, if you want to make a down counter, it is counting up. Same counter can be used for the down counter. There are two methods here. One method is simply taking output from the inverting terminal. By taking output from inverting terminal, same counter can be used as a down counter. This is one method. Another method is, instead of connecting here, we connect from here. That inverting terminal output connected as a clock pulse to the next flip-flop. Inverting terminal output connected as a clock pulse for the next flip-flop, and output will be taken as it is from the original terminal, true terminal. This is Q1, this one is Q2, this one is Q3. Output taken as usual. Then this also work as a down counter. So there are two methods here I have explained. One is simply taking output from the inverting terminal, or clock pulse, apply clock pulse from the inverting terminal to the next flip-flop. This can be used as a down counter. Okay, so we have explained you the down counter. Next I'll tell you that same counter by small modification with one NAND gate you can use as a modulus of counter. For example, if you want to design mod 5 counter, mod 5 counter means it should count only 5. But for the mod 5 counter, we require 3 flip-flop. 3 flip-flop means it should count 7 state, 8 state, but we want to cut short up to 5 only. So 3 we want to remove. The 3 state we can truncate by using the NAND gate. Just we are showing one example. Here I am designing one more 3-bit flip-flop. 1, 2. T flip-flop also can be used. T flip-flop also has the same property. I am using now here T flip-flop. T Q0, Q0 bar, T1, Q1, Q1 bar, T2, Q2, Q2 bar. We are connecting the clock pulse as usual. We are connecting clock pulse as usual. We are giving the clock pulse at the first, and T we are giving 1, T we are giving 1, T we are giving 1. That means it is all are in toggle mode. All flip-flop are in toggle mode. T flip-flop means whenever input is setting 1 and whenever you are giving here 0, it will toggle. This is the very simple characteristics of the T flip-flop. Now Whenever you give the clock pulse, it start counting as usual, but I want to truncate at the 6. So 6 means it is 110. Therefore, when output is about to come 110, that time it should be switched off. To make a switch off, we use one additional provision that is called clear input. Clear input will connect here, will connect clear input, and that clear input we give the NAND gate connection. We give the NAND gate connection. This NAND gate connection, this 110 output will connect. 1 1 and one output will connect with NOT gate. So all input we give here 1. When all input we give here 1 0 1 2. So whenever 1 1 0 it will come, this NAND gate will give the clear input to all the flip-flop and output will become 0. Therefore, this counter will count 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1. Again it is 0 0 0. So this is the modulus of the counter. So next we see synchronous. Synchronous counter, asynchronous counter, already difference I have explained you. So now I'll see how to design the synchronous counter. For designing the synchronous counter, method is same. All the method is same. Here also we have to use a state diagram, state table, K-map, simplification, Boolean expression, then last is the logic diagram. So to design a synchronous counter, we show you the video presentation so that it will be easy understandable. We are designing synchronous counter. So a step to design is, first we select the flip-flop. Here you are designing 3-bit synchronous counter. Therefore 3 JK flip-flop you require. 3 JK flip-flop, we make a first a state diagram, then a state table. Then after the state table, we go to the K-map equation, and after K-map equation, we design the, so first state diagram. So this counter will count first 0 0, next state is 0 0 1, next state is 0 1 0, next state is 0 1 1, next state is 1 0 0, next state is 1 0 1, next is 1 1 0, next is 1 1 1, and finally 0 0 0. So state diagram, here state diagram, present state 0 0 0, next state 0 0 1, state diagram explain. Same state diagram, we convert all the information at state table. Here we are using 3 flip-flop, so we are giving name, output name QC, QB, QA. Next state QC plus 1, QB plus 1, and QA plus 1. So 3 we are using 3 flip-flop, 3 flip-flop we have used, and whatever information was there at state diagram, we are transferring here. Present state 0 0 0, next state 0 0 1. Present state 0 0 1, next state 0 1 0. Present state 0 1 0, next state 0 1 1. So like this, we have to fill all this information at this state table. When filling all information at state table, next step will be excitation table. So excitation table we have to fill here. The excitation table of JK flip-flop is very simple to remember. Start from 0, present state, next state. When start from 0, K don't care. Very simple. Start from 0, K don't care. If there is a no change, J is 0. If there is a change means 0 to 1 is change. 1 to 0 is change. When there is a change, it is input 1. Start from 1, J don't care. When there is a change, it is 1. When there is a no change, it is 0. So this, based on this excitation table, we will complete that state table. By completing the state table, we are showing here JCKC. First, with same method, we are showing here start here 0, 1, 2, 3, 4. 3 place is 0, K don't care, don't care, don't care, don't care. There is no change, 0 to 0, 0 to 0, 0 to 0, 0 to 0, 1. So only one place change is there, here it is 1. Remaining, there is no change, so it is 0, 0, 0, 0. So with same method, we'll fill this flip-flop input table. So this is for the one flip-flop. Similarly, we'll fill for the next flip-flop, JB, KB, and similarly we'll fill for the next flip-flop, JA, KA. So all the flip-flop with the same method, we fill this flip-flop input table. After filling this flip-flop input table, method application is same. Now 0 to 1. Start from 0, K don't care. There is a 0 to 1 change, it is 1. Very simple to remember this. Start from 1, J don't care. 1 to 0, there is change, it is 1. Change means 1, no change means it is 0. So by this way, we are filling all the flip-flop input table. After filling all the flip-flop input table, next we require to expression. So 1, 2, 3, 4, 5, 6. We require 6 K map. By 6 K map, we fill all this. Now it is a min term. All this min term we fill into 6 K map. After filling 6 K map, we'll get 6 expression. After getting 6 expression, we'll design. So now we are filling that 6 K map. So this is the first K map, JC. First K map JC, we have filled the JC. Here 0, 0, 0, 1, don't care, don't care, don't care, don't care, fill. There is one pair we got, equation we got, QA, QA. Similarly, for the KC also same thing. These are the don't care and these are the 0, this is the 1. We have filled here. After filling here, we'll get the almost same equation we'll get here. Here we'll get 1. And equation is 1, 1, QA, QB, QA. So KC also QA, QB. JC also QA, QB. KC also QA, QB. Similarly, we'll do for the JB and KB. JB and KB, we are filling all this information on the K map. Filling all the information on the K map. Equation will get JB equal to QA. Here, this is the one quad we are getting here. So due to this quad, QA is common. So JB equal to QA. Similarly, KB also equal to QA. This one and this one is common, QA. So KB also equal to QA. So both equation we found, JB, KB. Finally, JA, KA. JA, KA equation also very simple. Here, very important to note that there is no 0 in this line. There is no 0 in this line. So don't care also can be considered as a 1. Don't care can be 0 or 1. So no 0, everything is filled there. After filling there, this 1 here and this don't care here. So this frame 1 octet. To frame 1 octet, resultant equation will be J equal to 1. J equal to 1. Similarly, Ka also does not have any 0. So see, it is a octet became. This octet gives the equation Ja equal to 1. Similarly, Ka equal to also 1. K equal to also 1. Here also it is 1 octet. So K also equal to 1. So finally, all the equation will keep at one place. All equation kept at one place. J equal to 1, K equal to 1, JB equal to QA, KB equal to QA, JC equal to QB, QA, KC equal to QB, QA. All equation we kept at one place. Final diagram is, finally we'll draw the diagram. It required 3 flip-flop, 3 flip-flop connected. After connecting 3 flip-flop, all the flip-flop given the common clock pulse, synchronous counter it is. So synchronous counter has a common clock pulse. Common clock pulse is connected to all the flip-flop. Now whatever equation is here, accordingly connect. Both J and K are 1. J and K connected to the common line. We have given J K equal to 1. Similarly, J, B and KB, it is QA. QA is here. Output of QA is here. So this directly you can connect here. We have connected JB equal to QA directly, and KB also QA. So this line we can extend, we can connect here the KB. So this equation also completed. JB equal to QA, KB also equal to QA. Coming back to the JC, JC is QB and QA. So there is a AND gate here. So AND gate, output of second, output of first, both flip-flop will be ANDed together and given to JC. So we are taking this one AND gate, one terminal taking from the QA and another terminal taking from the QB. This terminal taking from the QB here, and output is connecting to the JC. Output connected here JC. So one part is over, JC equal to QA QB, this part is over. Now KC equal to QB QA, KC equal to QB QA. So both are same. Here also same line we can connect here. Same line you can connect here. So this design completes, and after that output you can take from the QA, output you can take from the QB, and output you can take from the QC. After taking output from QA, QB, QC, it completes the one synchronous design. So we have explained here asynchronous counter, I explained asynchronous up counter, asynchronous down counter. Then we have explained the modulus of the counter. Then we have explained the design of the counter. So this design is, this also has one pattern. It is not necessary to do the design. It is always, it is a framed. But whenever you require to design uneven sequence like 3, 5, 4, 6, 9, for uneven sequence, when you require uneven sequence, that time actually design is very important, because this also you can remember, but uneven sequence will be given that you cannot remember. That time you have to remember complete. That is why it is important to learn the design. Method is same here. Method is same. So step one, state diagram. Step 2, state table. State table will contains present state, next state, then flip-flop input. Flip-flop input. Then third one is K-map. K-map simplification. K-map simplification will give the Boolean expression. By using the K-map simplification, we'll get the Boolean expression. By using the Boolean expression, we'll draw the logic diagram. We'll draw the logic diagram. With these steps, we can design any types of uneven sequence. It is not necessary to design, for example, we are designing 0 to 3. 0 to 3 we are designing, 0 to 3, 4. 0, 3 to 4, 0, 3 to 4. These are the 4 not, you cannot design 1. 2-bit asynchronous counter will design 0, 3, 2, 1 or 0, 2, 3, 1. 0, 2, 3, 1 will design here. So designing part is 0, 2, 3, 1. We are designing uneven. It is not a proper sequence. 0, 2, 3, 1 we are designing. So state diagram here it is 0, 0. Next state diagram is 0, 1. Next state diagram is 3, 1, 1. And next state diagram is 0, 1. So these are the state diagram. This state diagram can be, this is a 2-bit synchronous counter, can be converted into a state table, and the same method either T flip-flop or JK flip-flop excitation table can be used to fill this state table. After filling the state table, what method I have explained, by using K-map, we'll get the equation. After getting the equation, we'll draw the logic diagram. Therefore, we can conclude this. So counter design is one very important topic. Applications we have seen here. So the asynchronous design is little bit simple. but it is slow. But what is the importance? Why people still using asynchronous counter? Because battery consumption or power consumption is less in asynchronous, whereas synchronous is complicated, but power consumption is more. Synchronous is faster than asynchronous, but due to it has some own merit and demerit. It has own merit and demerit. So both design is important for digital circuit. So we'll conclude this today, and we'll meet next session as a random some another type of sequential circuit design. Thank you.